All right, so we just worked a really cool example problem here. Go look at that video if you haven't already. And let's continue on talking about the second law of thermodynamics. Now, if you remember from lecture 17, we said this is the second law in its purest, rawest differential inequality form, not even a differential equation, differential inequality form. And here we're saying that a change in entropy is always going to be greater than or at least equal to the amount of heat transfer divided by temperature. The limit, the equal to part of that inequality is where we have a reversible process where the change in entropy for a system is equal to the amount of heat transfer, the dq, the differential slice of heat transfer, divided by the temperature at which that heat transfer occurs. If I separate that equation, I move t over to the other side of the equation. Now I've got dq is equal to t ds. So for a reversible process, notice that q is equal to the integral of temperature with respect to entropy. And these should all be capital S's here. I don't know why they're not. Those should be capital S's. At any rate, similar to the fact that remember that work is equal to the integral of pressure with respect to volume. So if work is equal to the integral of pressure with respect to volume, heat, in the case of a reversible process, is equal to the integral of temperature with respect to entropy. Now, if we look at that graphically here, you can see that if the process is reversible to go from, I don't know, some state 1 up here down to state 2 down there, the area underneath that curve represents the total heat transfer to get from this temperature entropy combination down to this temperature entropy combination. If the process is not reversible, then well, you get a different path basically. But so this is kind of a cool graphic that you'll see. It's really just a graphical representation of this concept here. Okay. Now, another cool graphic we can look at is where I put enthalpy up here on the y-axis and entropy over here on the x-axis. And if we compare it this way, notice that the change in enthalpy, that's going to represent the potential work that could be extracted from a process like a turbine, or for example, here we have a compressor. The change in enthalpy, notice the first law simplified down to the work required for that compressor was based on the change in enthalpy. So the change in enthalpy here determines the work that could be extracted from a turbine or the work that is required for a compression process. And notice the change in entropy. The change in entropy basically measures, if there's no heat transfer, is going to measure the irreversibilities. So in this particular problem we had earlier, notice we got down here and we said that the change in entropy is 0. So for this process that we worked in the previous example, this would be a vertical line from state 1 to 2. It would go straight up and down. And to reach the same line of constant pressure, to reach the same exit pressure, you would have probably a much smaller enthalpy drop to get from point 1 down to point 2, as opposed to a real compressor that we would build or construct. It's going to have to go a longer distance, and it would actually go, in the case of a compressor, it would actually be going up to a higher enthalpy. This would be like for a turbine. So for a turbine, a real turbine would generate some entropy as it goes from state 1 to 2, from a higher to a lower enthalpy, to reach the same exit pressure. And so we'll talk, I think about lecture 20 or so, we'll talk about isentropic efficiency, where we actually measure kind of the difference between those two. So more on this to follow later, but it's a nice visual representation of something like, this is really kind of more for a turbine, where this is a compressor, which is kind of the reverse of a turbine. So it would be kind of the opposite of in this example compared to what you see on the screen there. So with that, all that in mind, again, our goal at this point is to really become familiar with the second law. All right. And the second law for a process from state 1 to 2 says that the change in entropy is going to equal this integral from state 1 to 2 dq over t plus the amount of entropy that's being generated. So I write this here so we've got it right in front of us. We can see it. There are three ways I like to talk about that we can determine a change in entropy, right? Delta S values, the left-hand side of this equation. There are three ways I can determine the left-hand side of this equation. The first is table properties. This works for water properties. Trying to talk and write at the same time. Sometimes that works, sometimes that doesn't. This works for water and R134, right? Note for ideal gases, you do have property tables for ideal gases. And when you go look at those tables for ideal gases, you'll notice that they give you this S, I call it S naught. You could call it S degree or S circle. When I see a subscript or superscript of a zero, sometimes I call it a naught. So that's S naught. That is not an S value. If you go look at the tables for water in R134, you get an actual S value. If you go look at the tables for ideal gases, they'll give you this S naught value, this S0 value. And some of the tables will also give you like an S plus value. We're going to talk about what we can do with these. These are not S values. You cannot plug those directly into the left-hand side of this equation for the ideal gases. Now, for water and R134, they will give you actual S values, just like we saw in this previous example. We were able to take S values right here for these values here, and we said, well, S1 is going to equal S2. And so when I found S1 on the table, that became the same as S2. So that worked. Okay. But for ideal gases, I'm going to have to do something different. And we'll talk about, we've got some options for that. The second way that I can determine delta S is what I like to call the second law itself, which is what we did in this last problem. I knew how to describe this term. It was zero. And I knew how to describe this term. It was zero. So I was able to use the second law itself to determine that the change in entropy is zero. And so that was a way that I could determine delta S. If I know everything about the right-hand side, I can use that to describe the left-hand side. So that is a thing that is allowed. The third thing that we're going to use is a tool that we call Gibbs equation. Gibbs free energy equation, they may have called it in a chemistry class. And it's the same principle. We're going to apply it a little bit differently, but it's there they were often looking at in a chemistry class, they're probably considering, is this process possible? And basically what they're saying is, well, would we have to destroy entropy in order for this process to work? Here we're going to do something very similar, but what we can do with Gibbs equation is it allows us to describe this left-hand side of the equation and use that then to determine unknown information about the right-hand side of the equation in specific circumstances. So that's more on that to come. Okay. So again, if we break these down, if we look a little bit at 1, 2, and 3 here, this is right. This is 1. Water in R134, we have table values for S values. And so that's, I don't think we really have to say much more on that. I've already said quite a bit. I'm just going to move forward. Okay. Again, the only thing is this caveat, S naught values you find in the ideal gas tables are not S values, so we can't use those. Okay, now if I go forward here, and again, if we look at the second law itself, using the second law itself, and the question is, do I know something about the heat and do I know something about the entropy generated? Right? If it's adiabatic, we've already seen that in this example we just worked, then the integral of dq over t, when I add up a bunch of zeros, I still get zero. So that's a really nice, easy thing I can do with this term. But maybe that's not the only thing I've got. What happens if I have heat transfer occurring at a constant temperature? So if I'm integrating dq over t and t is constant, then I can bring that out of the integral. And now I'm just integrating dq. Well, if I integrate dq, what do I get? I just get q. So this often is written this way. You'll see this notation in a lot of texts, where basically you're adding all of the q's in the in direction, subtracting all the q's in the out direction, and you're dividing each of those heats by the temperature at which that heat transfer occurs. If I have constant, and there are basically two main scenarios we're going to encounter in this class what do we do with this integral dq over t? Like I told you, we're not going to do a bunch of partial integrals. What do I do with this integral dq over t? It's either going to be 0 or it's going to simplify down to this where I have a Q divided by temperature. If it's in, it's going to be positive. If it's out, it's going to be negative. So add the heat in divided by temperature, subtract the heat out divided by temperature, and this quantity will take the place of this integral dq over t. If I have heat transfer in this class, it's going to be occurring at a constant temperature, or I'm going to have some other tool for trying to quantify this integral. In the rarest case, I think there's actually a problem in the homework where it basically gives you this heat transfer over temperature. I think it says something about the environment gains entropy at some rate, and they're basically telling you this quantity when they give you those words. It's kind of a weird way to write it. It's not how I would word it on a test problem, but you can encounter a situation where they'll give you this quantity, but otherwise, unless they give you this quantity in kind of a weird situation, your main options in this class with me are going to be it's either 0 or it's going to become Q over T, where in is positive and out is negative. What else do we do with the right-hand side? So again, do I know something about the heat transfer? These are my main options with the integral Q over T. It's either 0 or Q over T, right? What about the S-gen? Well, can I, like I did in this previous problem, they told me I'm looking for the minimum input, and that's where we said S-gen is 0. So that's a common thing we'll do with the entropy generated, is we'll say that it's 0. If the problem statement has told you, hey, this is the best possible version of this device, it's in the case of a compressor, it's requiring the minimum input. In the case of a turbine, it's generating the maximum output. In the case of a nozzle, you're getting the highest exit velocity because that's the goal of a nozzle is to increase the exit velocity. So these are different ways that we would encounter S-gen as 0. The other scenario that you might have to deal with S-gen is it might be what the problem's asking for. If the problem's, if it's a chapter 7 problem and it says, is this process possible? They're basically asking you, hey, do you have to destroy entropy for this thing to work? So if you calculate, in that case, you could just calculate S-gen, and it could be your unknown that you're solving for. And if you get a negative value, then no, the process is not possible. In a chapter 6 problem, if they're asking, is this possible? They're probably asking you to compare the efficiency to the maximum efficiency. But here in chapter 7, if they say, hey, is this process possible? They're wanting you to know, is it just destroying entropy? So you're basically solving for S-gen. So those are the two main things you'll encounter with S-gen is, do they give you enough information to assume S-gen is 0? Or do they give you enough everything else and you just solve for the S-gen? The S-gen is what you're actually looking for. In a rare, weird case, you could be given a specific value for S-gen. That's almost like has to be a textbook problem for them to do that. But it's not impossible mathematically. I mean, it's just fine. But those are how you deal with these terms on the right-hand side is if it's constant T, this just becomes Q over T. If not, it might be 0, or it might be what you're trying to find, basically. And then this guy is either 0 if it's a reversible process. You're looking for it, or in a weird situation, maybe they give it to you. Right? And then the third possible scenario is Gibbs equation. And that's a wonderful place to stop because that's going to be a derivation, a couple of derivations that we're going to have to work through. And I'm probably going to call that a good day for me, and I'll probably record the Gibbs equation another time. All right, guys. More videos to come.